The total probability log can also be extended for a general partition. Suppose there is a partition, n partition, where you are dividing omega into b1, b2 up to bn. Then the probability of A would be given by probability of bi into probability of A given bi, and then you sum it over all partition. So this denotes the probability of A intersection bi. So you have divided A into many parts by this partition, and this will be A intersection b1, A intersection b2, A intersection b3, A intersection b4. And if you add all those probabilities, you get a total probability of A. And the individual probabilities B given intersection, sorry, A intersection B1 is nothing but probability of B1 into probability of A given B1. Right. Now we will talk about independence. So we say two events A and B in any probability space are independent if probability of A intersection B is equal to probability of A into probability of B. So this is not always true, but whenever this is true, then only we will say that A and B are independent. So this is the definition of independence. If you are ever asked to know whether to calculate where two events are independent or not, you will just check whether the probability of their intersection event is equal to probability of product of their individual probabilities. So if the events are independent, then what will be the conditional probability A given B? Okay, let us understand this. So conditional probability of A given B is equal to probability of A intersection B divided by probability of B. Now by independence of A and B, the probability of A intersection B should be equal to probability of A into probability of B. So if you divide by probability of B, you just get probability of A. So this means in the case of where A and B are independent, probability of A condition B is equal to probability of A. Means conditioning with B does not change the probability of A. So that is why they are called independent, because when you condition that B has occurred, then you ask what is the probability of A is occurring. It is the same as if you have not conditioned. Okay, so that is why this independence we are saying. So both are valid formulas. Either you can prove if this formula that A intersection B probability is probability of A into probability of B, or if you prove that probability of A condition B is equal to probability of A. In both cases, they are same condition, and we will call that probability. We will say that A and B are independent. Okay, and this basically affect that the occurrence of B does not affect the chances of occurrence of A. So we will see one example. So let us assume you are doing two coin tosses together, and the outcomes are HH, TH, ST, and TT, and the probabilities are 1 by 4, 1 by 4, 1 by 4, 1 by 4. It means each of the singleton event has equal probability. Now, if we have consider an event where coin 1 shows heads, which is equal to A, HT, HH, and B is the event where coin 2 shows head, which is TH and HH, then the probability of A would be equal to half. The probability then, and probability of A condition B, which is probability of A intersection B divided by probability of B, is also half. So in that case, conditioning with B does not change the probability of A. So we will say probability of A is independent of probability of B, which here also implies that the chances that the first coin shows a head is independent of whether the coin 2 shows a head or tail. Okay, but you can verify that this is not always true if you have a different assignment. If these four outcomes are not equally probable, then you will see that if you condition on B, the second coin toss may change the outcome of the first coin toss, and then they would not be independent.